Anyways, the major reason that we talk about the kidney really is to understand how the blood is cleansed in the bloodstream. Okay, the blood is cleansed by the kidney basically by filtering it. Okay, and what it wants to do is basically remove a lot of the metabolic waste products out of the system, and it wants to remove acid that is produced as a normal process of metabolism. So the kidney is going to be really interested in doing this. What we talked about last week is that pretty much 20% of the blood that arrives at the glomerulus, about 20% of it is actually filtered. So it actually gets pushed into and becomes what we call urine. Okay? What's interesting about the glomerulus is that it's pretty much a passive filtration device. Okay? And the only thing that it can be a little bit selective about is size of the molecules that it does, that allows it to go across. So things that are negatively charged, it tends to repel, so it's more difficult to get rid of. So most proteins are negatively charged, so it kind of makes sense that you don't want to get rid of amino acids and proteins that easily, so you sort of want to retain those in the plasma, and you do. And of course, large macromolecules are not really wanted to be got rid of as well. So what you're seeing in the actual urine formation, the initial urine formation, is it looks very, very similar to plasma, except it doesn't have the macromolecules in it. It doesn't have things like proteins or large amino acid chains or things like mannitol if you give it. Okay? Usually doesn't get across the kidney in the first filtration. Some of it stays in your plasma. Now, that being said, a lot of the material that's in the urine is valuable stuff. You don't want to get rid of it, okay? Especially the things like sodium and water. So even though you just filtered 20%, you really don't want to lose 20% of volume every time the blood pumps to your kidneys. You'd be massively diuresing all the time. So that means the kidney tubules, which is when you look at them as a nephron, these tubules are going to have to do a major job of reabsorbing and pulling these macromolecules and micromolecules, like elemental things like sodium, potassium, chloride, back into the bloodstream. Okay? And that's what this discussion is more about. Okay? So chapter 4 is really beginning to describe what the tubules begin to do to try to alter the actual characteristics of the urine to eventually form either a concentrated or basically the dilute urine with all the metabolic waste products that it has in it. Okay? I'm not sure if some of you know that in people who go out in the ocean, the most common cause of death in the ocean, if you actually fall off the boat and actually survive in a life raft, is usually dehydration. And that's the most common reason people die. And sometimes people get really desperate and they'll drink their own urine. Okay? And it's really not a good idea. The reason it's not a good idea is because it is liquid, it's got water in it. Yeah, that's kind of fresh water. But the bad thing about it is it's full of toxins. Your body's gotten rid of all these things and does not really want to reabsorb it again. And then your GI tract will do a good job of doing that. If you ever are in a lifeboat, one of the things that you will find in a lifeboat is that they have Foley catheters. And you'll go like, why would they have that? And the reason they do that is that you can actually put the Foley catheter in the rectum, and then you push fluid, salt water, into your rectum, and that will actually absorb free water without absorbing the salts. And you can do the same thing with urine. Okay, so it's pretty much, of course, a dire situation. You want to be doing that for survival many times, but it is something that is possible. Okay? On the other hand, drinking urine will pretty much kill you at 30 to 50 times the rate if you just didn't drink at all. So you're actually better off not drinking. Yes? Salt water is still pretty bad. The osmolarity of salt water is very, very high. So it'll make you even more dehydrated. What will happen is if you drink a bunch of salt water into your stomach, is as soon as it gets into the intestinal tract, water that's in your plasma will get pulled into your GI tract, which then gives you diarrhea, which is the worst situation to be in. And it makes you even more profoundly dehydrated, and you go into profound shock much more rapidly. That's why we do it in the rectum. The reason you can do it in the rectum is because you bypass the absorption of the salt. Okay? If the salt gets too high, what ends up happening, of course, is you just, excrete it out your rectum right away. but you will absorb a certain degree of it. Okay? So when you're looking at epithelial cells, when you're looking at molecules moving, you have to think about diffusion once again. And when we're talking about the proximal tubule, which is most of the work is done to reabsorb stuff, this tends to be following diffusion principles, but it's going against gradients. So this area requires a lot of ATP for this to take place. Okay? Diffusion, of course, still follows true in the sense that if you are able to make a concentration gradient and allow the molecules to move down a concentration gradient, they will do that passively, which is what Fick's law is talking about. Fick's law is basically the rate of diffusion is dependent on the concentration gradient. If you have the concentration gradient on one side, it will push the molecules across to the opposite side. Graham's law basically states something similar to that, but it has to do with molecular weight, okay, which is the rate of diffusion of a gas, but in this case it would be the molecules in your urine, is inversely proportional to the square root of the molecular weight, which means that the larger the molecular weight, the less likely it's going to want to transfer across back into your bloodstream from urine. So diffusion is dependent on concentration gradients, it's dependent on molecular size, it's dependent on ionic charge and lipid solubility. It's also dependent on the permeability of the substance, membrane thickness, and membrane surface area. Okay? And if you think about it, most of us function just fine with 2 kidneys. So even if we lose 50% of our kidney function, we still function adequately. So we have quite a bit of reserve capacity in our kidneys. Okay? Some people, unfortunately, are born with a single kidney, and of course that means their membrane surface area has already been reduced by 50%, and you won't even pick up that they have any problems until they get into some kind of situation where they become dehydrated or they don't get adequate perfusion, and then all of a sudden they will unmask that they do have a renal function problem underneath. Now, when you're looking at crossing the epithelial cells, it's moving through channels. Okay, this becomes biologically an important concept because what are channels? Channels are formed by proteins. Okay, and as a consequence, you can construct different size channels depending on what molecule you want to get across. Okay, and that alone can make it selective as to what molecule you want to come across a membrane more easily. Okay? Basically, if they don't have the actual channels, then it must travel through the opening in the lipid membrane, which is not usually present. So the only opening you usually have is through one of these channels, which are protein pores. If you have a lipid-soluble agent, on the other hand, does it really matter if you have channels or not? No. If you look at our anesthetic agents that are lipid-soluble, they're minimally removed by the kidney. And because as soon as they get into the urine, they do diffuse they filter really easily through the glomerulus. They have no problem getting across into the urine, but as soon as it gets into the proximal tubule, they'll rapidly reabsorb through the lipid membrane. There's nothing really that will hinder their reabsorption rate. Okay. So when you're actually looking at some macromolecules that you do want to pull back selectively, you're looking at specific protein channels or specific protein transporters. Now, there's a difference in that wording. It's very subtle. One's a channel. What's a channel usually mean? It's passive. It tends to go down a gradient. Or you may have an electrostatic field that's developed, and that it helps move a molecule across. So it tends to be a passive event. Okay? On the other hand, transporters tend to be ATP driven. So it requires energy and work. And that should make you concerned, because anytime you make something ATP driven, it means that it becomes more susceptible to problems. Okay? Anytime you require energy to make something work, it's more likely to break down. If you think about it, what's easier to fix? A scooter where you push yourself around, or a car that has an engine and for some reason the engine doesn't start and you have no clue how to restart it. Okay, versus a scooter, the little wheel falls off, you know how to put the screw back in and off you go again. It's not a big deal. Okay? But channels that are transporters, once you mess them up, it's hard to get them back. And that's what we call ATN to a certain degree. Now let's look at protein channels. The protein channels are passive devices that tend to have specificity is usually very low. And the reason that specificity is low is because it tends to be molecular weight dependent. Okay? It's like saying that this door right here is passive. Okay? So if I come through this door, I can open it, and I can get out of here really easily. Okay? Pretty much everybody in this room can walk through that door. Okay? So that means it's not specific. But if I have somebody who weighs 450 pounds, who basically cannot walk through the door because physically they're too wide for the door, that means I'm specific for the molecular weight for that individual. Okay? They're too large to get across. Now, most substances move across due to gradients, and the limit crossing over is based on the protein structure of the channel. So in other words, I can charge the channel pore with a certain characteristic. If I want negative molecules to get across, what would I do to the inside of the door? What would I want to charge it with? Positive, right. Otherwise, I want to inhibit a protein or an amino acid which is negatively charged, then I would charge the door with a negative charge. It would repel that molecule. Does that mean that all molecules that are negatively charged will not get through that door? No. It just means that it would be more difficult for them to. Because still, based on their molecular weight, they're small enough, even though they're charged, they will still get passed. But just not in as great a numbers as something that would be charged and pulled into the vortex. Okay? There's different kinds of types of things that we talk as protein channels. We'll start making them go from protein channels, we'll call them sodium channels. But sodium channels are basically protein channels. Okay, so are chloride channels, and so is potassium channels. And there's also things called aquaporins that basically allow only water to come across, or mostly water to come across. And the movement can be controlled by the presence of a channel pore. In other words, you can actually change the configuration and you can lock the door. Okay, I can open it or lock it sometimes. Sometimes we can add voltage, channel things to it to make it more difficult for the door to open, or I can physically alter the channel so it doesn't open for certain reasons. On the other hand, protein transporters are very specific. They consume energy. And because they consume energy, they require a lot of ATP. And so that means that those channels are oxygen hogs. They're going to start consuming high levels of oxygen. So if you have a cell that's very dependent on protein transporters, one thing they also are going to become dependent on to do their work is ATP, which that means that they're very oxygen sensitive. If you don't provide the kidney with enough oxygen to it, those are the cells that die first. Okay? Not the rest of the tubule that doesn't care, that's more passive, the one that actually is doing the cuboidal workload, which is the cuboidal cells, which are in the proximal tubules, those are the cells that end up getting damaged. Okay? Now, because they require energy, it means that it takes a certain amount of ATP to bind to it and then cause the channel to change configuration. And all this takes milliseconds, and I'm talking about super milliseconds, but it takes a little bit longer than a channel pore. And because that, it tends to be slower. Okay? And these types of protein transporters can be either uniporters. Uniporters means they only carry one molecule across at a time. Then you can have what's called symporters. Okay? Symporters take two molecules across. And what's really cool about symporters is that some of them will take a molecule that's going down a gradient to pull the other guy across that's going up a gradient. Okay? That's pretty neat. Okay? So you can actually break down some of the workload. Other systems are called antiporters, which means that if you pull in one molecule, you export the other molecule out to sort of maintain the charge. A great example of that is the sodium-potassium ATP pump. Okay? If you look at potassium and hydrogen antiport systems, for every one hydrogen ion that I pull in, what happens to for every potassium ion that I pull in, what happens to my hydrogen ion? Goes out, so it goes in the opposite direction. Okay? And these are all use ATP. Then there's also weird things, which are rare, and these require super heavy workload. These are what's called receptor-mediated endocytosis, or transcytosis, and they're basically grabbing huge macromolecules, pulling them back into the cell, which then breaks them down in a coated vesicle and eventually extrudes this material back into the plasma. It usually is never functional at that point. The molecule has been broken down to enough point that it's inactive, but this is how some hormones will actually terminate in action. So let's look at this from the standpoint of the glomerulus. Remember, the hydrostatic flow is the pressure that's generated inside the glomerulus, which helps move molecules across into the proximal tubule. Okay? That hydrostatic pressure is what drives most of the particles through the membrane. It's not all of it, but a big majority of it is. Okay? And it's almost equivalent to the degree of filtration. Of course, what actually prevents a certain degree of filtration, of course, is the number of proteins that are in the plasma. They're actually pulling fluid back towards the blood capillary. And you also have sometimes, but very low amounts, usually don't have oncotic pressure, which is proteins on the opposite side of the kidney tubule, which then would pull more water that way. So that's usually not the case. It's mostly hydrostatic pressure that's really pushing fluids forward. The other thing that would prevent fluid movement forward would be an obstruction of the ureter or in the nephron. Why would that be the case? And the answer is because the intranephronic pressure goes up and exceeds or is equal to the glomerular pressure, and then filtration stops. Okay, so if you have a complete obstructed nephron, your filtration system terminates at that point, which is not good. That means that the kidney can't wash out the debris that's in the nephron, and then you may have problems later down the road. If you look at osmosis, remember we talked about this before, this is a passive situation, and basically osmosis is describing where salt goes, where water goes, and water goes where salt is going. So wherever the salt is, that's where water is going to go. It depends on a semi-permeable membrane. So if you have an impermeable membrane, can osmosis take place? The answer is no. You have to have a semi-permeable membrane for this to be able to happen. Okay? A classic example of describing osmosis is taking a flower, putting it in a vase, and then take in the vase, put a bunch of salt water in the vase, and watch what happens to the flower. Well, in that situation, this flower would crenate, which means it would basically get smaller and basically get wrinkly because the water would be pulled out of the plant into the salt solution. Okay? You could reverse it as well by just putting free water in the vase, and you'll actually see that the flower stays much longer alive than you expect because now water is going to go where salt is, which is in the cells of the plant. So it can go either way depending on just where the salt is concentrated at. What's important about osmosis is that it's a very important mechanism by which the kidney controls water. Most of the water that's reabsorbed from your kidney when it filters is in the proximal tubule. About 60% of the water that it filters is pulled back almost immediately in the proximal tubule. And people say, well, is there aquaporins? Is there devices that pull water in? And the answer is no. It uses osmosis. Okay, what it does is it pulls sodium against a gradient towards the capillary side, and as a consequence, water follows suit. Okay? So osmosis can be pretty important to hold water back in you. If you look at oncotic pressure, that's where proteins are, and proteins are important in the sense that they hold fluid inside your blood vessels. So loss of proteins is actually pretty dangerous if you have any kind of disease. What will happen is if you have a drop in oncotic pressure is that most people will develop peripheral edema. They will also develop a place where the kidney is now beginning to diurese more than it should. And as a consequence, the person will become even more profoundly dehydrated, okay, which could be adding to the situation. Even though it kind of, if you look at the person's legs, or edematous in the legs, that doesn't mean that they're not dehydrated. It's the intravascular volume that you really care about when we're doing our cases. If you see somebody with peripheral edema, and then you also see that they're spilling proteins in their urine, be concerned that that person could be very profoundly dehydrated and could cardiovascular collapse on you on induction. Okay? I love this picture. I don't know if you've ever seen this before. This is the picture of what the Bowman's capsule looks like. This is the afferent arteriole coming in, and then it goes into the capillary network. The reason I like this picture is a three-dimensional image of really showing you how it goes from an arteriole to a capillary network, which is very thin, and all of a sudden it goes back to the efferent arteriole going out. But what's interesting about this is that Bowman's capsule is where the urine's forming. Okay, it is a capsule. It is basically like a bulb with inside in here are like tree roots. Okay, and where the tree roots is actually what's giving the plasma or going to the fluid that goes into urine. So everything in this black in this picture should be actually yellow for urine that is formed. Now, transport mechanisms in reabsorption, most of the transport is due to reabsorption, especially in the proximal tubule. Okay? The reabsorption of water and almost all the solutes are linked directly or indirectly to the active reabsorption of sodium, which has to do with osmosis once again. All reabsorptive processes have a limit, which is an issue, okay? Which means that you can overwhelm the system. If you look at sugar, when we showed you this picture last week, okay, of actually what happens to sugar concentration, by the time it leaves the proximal tubules, what happens to sugar levels in the urine? It should be 0. Because glucose is something that your body desperately needs. It doesn't want to get rid of it. Okay? So in the proximal tubule, usually the body reabsorbs that very aggressively. Okay? But if I give you a lot of sugar to eat, or I make you a diabetic and your sugar control is too high in your bloodstream, and I overwhelm the transport mechanisms, instead of having, let's say, 150, 200 urine entering into the actual proximal tubule, I'm hitting it with 400 to 500 milligrams of glucose. Then I hit what's called the Tmax. Right around 300 to 400, the Tmax means that I cannot push any more glucose across, and I'm going to begin to spill glucose in that situation, which would be not a good thing. Okay? Because once glucose spills, what happens with water? Water follows where glucose is going as well, besides salt. Okay? So you begin to cause a diuresing effect. That's why diabetics are always dehydrated. You ever thought of that? You know, why are they dehydrated? They're not really losing sodium. They're losing a lot of free water, though, okay? Because their glucose is basically causing a shift of pulling water out of them. So if you look at the actual basic renal processes, you can break them down into 3 major parts, and eventually it ends up leading to the final answer, which is urine excretion. Okay? Urine excretion is equal to glomerular filtration plus tubular reabsorption, okay? Minus tubular reabsorption plus tubular secretion. That's really your urine excretion rate.